from 2017 to 2022. The project attempts to use unique and innovative approach and employ ecosystem-based assessment instead of element-based assessment, and addresses both flow and stock-based assessment. It is also evaluates blue carbon in an integrated land coast ocean scheme or multi-scale assessment, and develop an integrated model systems for coastal ecosystem under combined local and global environment threat. And finally, in line with the theme of the webinar, the project will attempt to develop a science-based policy, we call it named Blue Carbon Strategy, which is an effective scheme for properly conserving multiple ecosystem services, including blue carbon. In closing, I hope that all of you will enjoy the workshop and obtain new information as well as perspective on how various scientific aspects related to blue carbon can be used to support climate change and conservation policies. And finally, in the name of Allah Subhanahu wa Ta'ala, I declare webinar with the theme, the role of blue carbon science in supporting climate change and conservation policies, is officially open. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you for Professor Syarif Wijaya, who is willing to prepare the recorded opening remarks. And now we are entering the main sessions of the webinar today. And actually this webinar is divided into several sessions. The first one is what we call it policy sessions. There will be 2 speakers, and then it is followed by keynote speech, 1 speaker, and then the last session will be technical sessions. So for the policy sessions, the first speakers, we have a special guest here, Dr. Saiful Anwar from, he's a director of Greenhouse Gas Inventory and Monitoring, Reporting and Verifications, Directorate General of Climate Change, Ministry of Environment and Forestry. And he will be delivering his expert opinion and talk on the potential role of blue carbon in REDD+ and NDC. So, Dr. Anwar, the floor is yours. Please.
Thank you very much, Chairs, Dr. Noviadi, yang terhormat Bapak Kepala Badan, Prof. Syarif Wijaya, yang berada di Bali, Snow in Bali, distinguished research fellows, colleagues, friends, ladies and gentlemen, good morning. It is my great pleasure to be here in front of you in this Blue Carbon webinar to present the potential role of blue carbon in REDD+ and NDC as requested. In this coming presentation, I would like to share with you on how Indonesian effort to incorporate blue carbon, in this case mangrove, into REDD+, with particular reference of FCPF project in East Kalimantan, and look at possibility into NDC as well. Can I have my presentation, please? While waiting for the presentation, well, my presentation will begin with very basic about REDD+. and NDC, which is sound familiar but may be misleading in some cases. Next, please. Yep, thank you very much. So the first is with very basic questions about REDD+ and NDCs, which I mentioned sound familiar for all of us, but maybe misleading in some cases. Then we will briefly look at the importance of mangrove forest and move on to see how to mainstream blue carbon in greenhouse gas inventory. And finally, to observe the challenge and next improvement to incorporate blue carbon into NDCs. Next, please. REDD, what is REDD and NDCs? REDD stands for reducing emission from deforestation and forest degradation in developing countries, while plus include sustainable management of forests, conservation of forest carbon stocks, and enhancement of forest carbon stocks. So REDD+ was first negotiated under the UNFCCC Framework Convention on Climate Change in 2005 in Montreal, with the objectives of mitigating climate through reducing net emission of greenhouse gas emission through enhanced forest management in developing countries, previously called avoiding deforestation. So REDD+ is one of the schemes to achieve NDC's target as well as SDGs. The other is like carbon credit, among others. And what is NDCs? NDCs are the heart of the Paris Agreement and the achievement of these long-term goals. The Paris Agreement requests each country to outline and communicate their post-2020 climate actions known as their NDCs, National Determined Contribution. In 2015, the government of Indonesia pledged to reduce emission from 2020 to 2030 by 29%. It's unconditional against the 2030 business as usual scenario. Next, please. Why is REDD matter? Why maybe attractive to someone, but not others? Funding opportunities are usually the reason for wanting to participate in REDD implementation. So there is a result-based payment as mandated in Article 5 of Paris Agreement. It's not Article 6 about carbon credit, which is still in process. However, in order to obtain and receive result-based finance for results from the implementation of REDD+ activities, developing countries parties should have the following in place. First is a national strategy or action plan, an assessed forest reference emission level or forest reference level, and a national forest monitoring systems, and then systems for providing information on how the safeguards are being addressed and respected. And the result-based action should also be fully measured, reported, and verified. And of course, we'll have benefit sharing plan or share of proceed. Payment of funds are received not by Ministry of Environment and Forestry, of course, but by the Environmental Fund Agency, we call it BPDLH, and distributed accordingly to beneficiaries based on benefit sharing plan. The funds goes to the actors who already reduce emissions, but not simply like planting one mangrove trees and get money. No, it will be monitored through satellite or whatever to see the changing of the mangrove coverage, then reported and verified by independent verificator. So next, please. The role of blue carbon in REDD+. So blue carbon refer to carbon dioxide removed from the atmosphere by the world coastal ocean ecosystem, mostly mangrove, salt marshes, seagrass, and potentially microalgae. With the description previously about REDD+, which blue carbon could be incorporated into REDD+ so far. Which one is must be, yeah, of course, mangrove forest. All requirement of mangrove for REDD+ is in place, and part of so mangrove will be part of deforestation and forest degradation scheme. This is under the IPCC 2013 supplement guideline. Next, please. Yes, so the state of the art of Indonesian blue carbon with regard to data blue carbons. Indonesia's coastal carbon storage is huge, about 3.3 billion ton carbon, yeah, not CO2. And next, please. And also already mentioned by Professor Pak Kepala Badan, Indonesia has the largest mangrove cover in South Asia and in the world, cover about 20% of the global total mangrove area, and 43 species of tropical mangroves are found in Indonesia, or represent 80% of tropical mangroves in the world, according to FAO. This will give a really significant influence in tackling climate change. Next, please. The mangrove has been incorporated into National Greenhouse Gas Inventory. So according to IPCC guideline, for national greenhouse inventories about wetland, a mangrove is part of AFOLU, agriculture, forest, and land use. So parties are encouraged to develop lesson learned and experience on greenhouse inventory and mitigation actions. So carbon pools for greenhouse gas inventory or carbon accounting in mangrove ecosystems, at least there are 3 pools: above ground pools, above ground biomass pools, and below ground biomass, and soil mangrove. And could be another pools, it's like that organic matter. Next, please. Mainstreaming Indonesia blue carbon in national greenhouse gas inventory. In national inventory, mangrove forest is already including in 23rd land cover classes in the first FREL, forest reference emission level. And also carbon stocks of above ground mangrove, this pools, one of the pools above ground mangrove biomass, by its primary as well as secondary forest, it has been also included. However, for mangrove soils, not yet included. Next, please. Given the importance of soil carbon in mangrove forest ecosystems, Indonesia improved its greenhouse gas inventory or accounting system to address soil carbon in mangrove soils by improving second FREL, second forest reference emission level for 2020-2025 in terms of emission factor of mangrove forest. The benefit of this improvement is increasing accuracy and reducing uncertainty from soil carbon emission factor, identified potential of soil carbon sequestration accurately, and improve allocated national FREL to the subnational. Next slide, please. The obstacle that Indonesia has encountered when incorporate mangrove into greenhouse gas inventory, however, there are some examples of obstacles. The sampling number of analysis, accuracy and uncertainty in mangrove forest cover change is still limited. And estimation of accuracy and uncertainty in mangrove forest cover change in each period depend on the quality of satellite imagery data and the analysis of detailed classification in mangrove forest cover, like low, medium, and also high density. And also, this is important, high cost for mangrove forest inventory. The level of accessibility. It's not easy like in the terrestrial forest. So what was done to overcome them, have planned to add the permanent sample plot as sampling number of mangrove forests to support increasing accuracy and reducing uncertainty, and cooperation to provide quality satellite imagery data, and reclassification of mangrove forest cover. Next, please. This is the example of ER through REDD+ scheme in ERPD. ERPD is a emission reduction project document of the FCPF Carbon Fund project in East Kalimantan. So Indonesia has incorporated mangrove forest into ERPD of East Kalimantan. So this is a REDD+ scheme. So more specifically in Mahakam Delta. So the delta is the outlet of Mahakam River. So the green circle shows each Kalimantan province, and red color in the rectangle is Mahakam Delta. You will see the condition. The next of the next slide, please. So this is the picture mangrove deforestation. This is from Ms. Arifanti. So clearing of mangrove trees and draining mangrove soils. This activity led to 45% reduction of soil carbon stock. And next, please. So mangrove forest has, as I mentioned, incorporated into ERPD REDD+ through several steps. There is a process as well. So the first is analysis of the driver of deforestation and degradation in mangrove forest, and analysis of drivers underlying causes of deforestation and degradation in mangrove forest, and analysis of reference level historical emissions in mangrove forest, and establish the emissions reduction program to address the drivers of deforestation and degradation in mangrove forest, and establish the safeguard to address the impact of emission reduction program. Next slide, please. So this slide the emission reduction from mangrove soil in East Kalimantan. So it is expected that emissions from mangrove soils can be reduced by 25% by the 5 years of program implementation. Sorry. So that is in 2024. Total emission reduction of the payment agreement period for protection of mangrove are expected to be 0.8 million ton CO2 equivalent. Challenges to improve in mangrove monitoring and reporting for greenhouse gas inventory. Of course, reducing uncertainty. It means a better estimate of carbon stocks, like how much carbon loss in mangrove due to disturbance event, and how the magnitudes of change post disturbance events. And also improving emissions estimates to apply full carbon accounting model, or which is able to track the flow of carbon for different carbon pools, especially the flow carbon to soil pools. Next, please. So several papers has been published related to mangrove emission factor of greenhouse gas. Arifanti 2019 reported the first tier 3 emission factor for mangrove conversion to aquaculture for Indonesia. And Murtiarso also highlights the potential of conserving mangrove to reduce emissions. And also Arifanti again reported the first emission factor for mangrove conversion to aquaculture for Indonesia is about 120 ton CO2 equivalent per hectare per year. So this emission factor will be incorporated in the ARPD's technical correction. Next, please. Another existing knowledge. So from CIDIC, CIDIC compare the carbon sequestration in restored and abandoned ponds. She concluded that a greater potential for climate change mitigation can be achieved by increasing conservation area that keep mangrove forests from land conversion. Next, please. Research and innovation is still needed for monitoring mangrove ecosystem carbon dynamics. So like stock different method and gain loss method and others. So next, please. I will be fast. And now talk about NDCs. Sorry. I think this another. Next, please. Oh, I think there is another slide missing. Sorry. Okay. All right. Now to national level challenge to include NDC. Yes. The challenge to include blue carbon in an NDCs are, you see the rate of degradation of coastal wetland ecosystems is higher than the rate of rehabilitation. There will be questions of achieving NDC's target if it is included. And limited information and data availability on seagrass and other blue carbon ecosystems, including activity data and methodology to calculate emission factors, and also land tenure conflicts in mangrove converted aquacultures, and the implementation of co-benefit and outcomes for livelihood. So as you understand that NDCs is not merely climate change mitigation, but also climate change adaptation. So with the target of coastal and marine ecosystem climate resilience is really target of NDCs in adaptation. So foundational principle of the strategic approach of Indonesia's NDC is promoting climate resilience in food, water, and energies. So as mentioned by Kabadan, so Indonesia will improve its management of natural resource to enhance climate resilience by protecting and restoring the key coastal and marine ecosystem. This is in NDC's adaptation. So next, please.
2 more minutes, Pak Saiful Anwar.
Yes, we are approaching the end of my slide. So the next improvement, I think this slide is changing the font. It's a bit different. That's no problem. So the next improvement for mangrove ecosystem, first identify and compile of activity data in below ground biomass mangrove. And second, develop a methodology of soil carbon, tiers 2. And third, calculating non-CO2 of above ground biomass from forest fire and pit fire. And also research on pit decomposition of mangrove ecosystem based on high of water level. So including all significant carbon pools and monitoring change in mangrove carbon stock should be considered for future improvement in national carbon accounting and reporting for greenhouse gas inventory. For seagrass ecosystem, need develop complete map of Indonesian seagrass. For example, one map of seagrass that cover all Indonesia coastal area in time series. And the second, identify and develop an activity data and emission factors. And the third is research and other potential research on other potential blue carbon. The next slide, I think this is the end of my slide. So we have to protect mangrove from conversion. We have to restore degraded mangrove forest for environment and people. And we have to achieve NDC targets. So that is from me. I apologize for my prolonged presentation and the inconvenience. So I give back this floor to Dr. Novi, and I thank you.
Thank you very much, Dr. Saiful Anwar, for the insightful presentations on the role of the potential role of blue carbon in REDD+ and NDC. So for the participants, if you have any questions to any speakers, including to Dr. Anwar, please type in your questions to the chat box, Q&A chat box at the bottom of the web. Please make sure that you mention your name and affiliations and the names of the speaker to whom you direct your questions. And of course, the most important one, your questions. Okay. So during the webinar, the speakers will try to answer your questions. And for Dr. Anwar, I heard that you have some other commitments, but of course, it will be a pleasure for us if you could stay with us during the webinar. But if you have other commitment, then thank you very much for your time and presentations. And
thank you, Pak Novi. I should leave. It's already called me several times. Thank you.
Thank you. And the next speaker, a special guest from our Ministry of Marine Affairs and Environment, Mr. Andi Rusandi, who is now on duty in Bali. And he will be presenting on the marine protected area in Indonesia, progress and outlook. Mr. Andi Rusandi is the Director of Conservation and Marine Biodiversity, Directorate General of Marine Spatial Management, Ministry of Marine Affairs and Fisheries, Indonesia. And Mr. Andi, you will have 15 minutes time for presentations, and I will ring a bell when you reach your last 3 minutes of your presentation. Sorry, I forgot to use this for the previous speaker. So, Mr. Andi Rusandi, please take the floor.
Thank you, Pak Novi. and then good morning in here in Bali for everyone. I'm happy to be here for share about the status of Indonesia Marine Protected Area policy. We are going to talk about this matter. We have only 10 slides, Pak Novi, and then everyone, and then we have to take, I hope, not more 15 minutes. Okay. This is a marine Indonesia Marine Protected Area, and then next, please. Okay. Indonesia has 325 million marine areas. This potency has reach of marine biodiversity. Therefore, to ensure this nature resources is sustainable, the government of Indonesia committed to protect certain marine area as MPA. This policy accordance to international mandates such as CBD, Aichi target, SDG 14, in term to protect 10% of marine areas as MPA. Until March 2020, Indonesia have reached 23.38 million hectares, or approximately 7.19% from global mandate. In 2030, Indonesia through MMAF has announced to achieve 10% or equal to 32.5 million hectares of national water as MPA. Furthermore, for the next 5 years or in 2024, we are targeting 27.1 million hectares of MPA will be gazetted. The MPAs in Indonesia are managed by national and provincial authorities to ensure the MPAs run effective. We evaluate those MPA by using MPA effectiveness assessing tools, or we know EKKP3 tool. In 2019, around 40% that we have reached the green level status. Green level status is indicating the MPA management effectiveness on minimum management condition. Thus, we are trying to enhance the level effectiveness and pointed to year of 2024, 20 million hectares of MPA will be the level optimum management status. These levels show the MPAs has advantage to biodiversity and community. In 2030, this MPAs has roles the protected biodiversity and fish resources and improve the welfare of fishing communities, coastal and small island. Thus, the MPA will be designed with approaches that are based on knowledge, designed to support a resilient ecosystem, support sustainability, sustainable fish resources, and contribute to the local national economy. Next slide, please. We are talking about measuring by Indonesia territory sea. If we measuring based on territory sea, 0 to 12 nautical miles, our MPAs have reached 15.5%. That show the target 10% has achieved. The map show the distribution of MPA in 34 provinces. The graph shows there are more 10 provinces already preserved more than 10%, and the largest contribution is West Papua with already 38.3%. It causes Raja Ampat MPAs and Kaimana MP have large area which has most diversity of coral reef and fishes. Nevertheless, we still targeting in improving the effectiveness this MPAs management, especially to give more benefit to communities. Next slide, please. Now we are talking about the challenge of development and managing MPA. There are various challenges that facing by Indonesia government to manage and develop the MPA, such as human activities, gap between policies and regulation, human resources, and finally is financial. We are trying to harmonize the regulation of conservation and sustainability fisheries management, since the MPS must also maintain the stock sustainability. Next slide, please. How about Indonesia MPS apply zoning concept? We have a concept for zoning. In Indonesia, the MPA managed by zoning system. This system to give the access for local community to utilize the benefit that provide by the MPA. There are 4 types of zoning in MPA. First, for zone is fully protected, only allowed for research and education. And then limited use zone can be utilizing as marine ecotourism, sustainable fisheries zone for fisheries activities that following the sustainable fisheries rule, and other zone that use for rehabilitation and protection the environment. Expected by implementing zoning system, the condition of biophysics of MPA can be improved, strengthening the government and enhance social, economic, and culture, particular in local community. And then how we have next slide, please. Okay, and then this slide we are talking about program and strategic how to develop MPA for effective. MMAF was formulated 9 program to an outcome to overcome the issues on development and manage MPA effectiveness that are establishing new MPA, fulfillment MPA infrastructure, human resources, the availability of data series, surveillance, mitigation involving the local community, and sustainable financing. Meanwhile, we have 3 strategies related to increase the effectiveness of MPA management, which are sharing planning, sharing enforcement, and sharing responsibilities. Those strategies are selected because we identified the resources valuable for those who depend on the resources. Key stakeholders such as fishermen, tourism, mineral, and NELS. This is important because until now we have 197 MPAs separate in our country. Next slide, please. How to roadmap about MPA to 2030. Following the announcement of this new target at the OOC, MMIF was made collaboration with key government, NGOs, partner to produce MPA vision strategic planning for the next 10 years, with starting now in 2020. We have 7 topics to scoping the area of work, which are harmonized the planning among central, because we have province and then center government, so we have to harmonize about the planning, design, regulation, and policy, improve of human resources, utilization fisheries and sustainable tourism, sustainable financing, other effective area-based conservation measures, and communication platform development. With these 7 topics, we are expecting that effectively manage MPAs secure critical marine habitat, essential for ocean health. The MPAs available to to supply refuge for endangered, threatened, and protected species, and protect the breeding and nursery ground of commercially important fishery species. Moreover, MPS can be support the building of marine biomass and subsequent restocking of fishing ground through the spillover effect. We try to learn about how far spillover have effect to the other MPA, supporting livelihood and food security for millions globally. Finally, the MPAs provide a range of vital ecosystem services to coastal population, as well as preserving culture and natural heritage for oceanic nations. Well-designed and managed MPA network also support climate change resilience in rapidly changing marine environment. Next slide. And then we have also make a roadmap MPA from 2020 to 2024. We have formulated the 7 area, the important of in the next 5 years planning, which each year we produce the output. In 2020, output is to develop the stakeholder communication mechanism, identification of capacity building needs, integration of fisheries indicators in area management, integration of development planning and budgeting. In 2020, first, procure of management facilities and instructor optimization of funding source from PNBP. PNBP is like some money from the MPA come to the government. OAC introduction, strengthening of communication platform. In 2022, strengthening human resources, developing a structured capacity building program, development of regional incentive fund. We try to give some reward for province, like money go to the province who province can be managed well for MPA. In 2023, transfer knowledge between regional personnel, strengthening of the training system through SKKNI and SK3, take development, OACM progress reporting, and then in 2024, capacity building program monitoring, development of a strategy for retaining personnel, OSM impact monitoring, and campaign strengthening. I think this is a good important thing about campaigns, about important for campaign. And next slide. And then in this slide, we are talking about conclusion and recommendation. As I explained on my presentation, we already achieved some target, yet we still have challenges. However, we committed to achieve national and global target in terms preserving 10% of marine areas MPA as MPA. Moreover, we developed the program and strategy to increase management effectiveness of MPS. The studies and research are required to respond the role of MPA that has impact to prosperity of communities. For that, we recommended recommend to all participants here to support us, particularly research agency, for developing first studies potential location for new MPA that also support for sustainable fishery. Second, studies of the status and trend conservation target, carrying capacity in MPA, environment impact assessment, and the last, alternative livelihood for communities and impact by the MPAs. I think that's it, our presentation for all here. We hope we get a suggestion or a comment, and then anything we try to respond. Thank you, Pak Novi.
Thank you very much, Pak Andi Rusandi. Perfect timing. Yeah.
Thank you.
A few seconds to the last 15 minutes. And for the all participants, please, if you have any questions to the previous speakers, just type it in the Q&A chat box at the bottom of the applications. Please mention your name and affiliations, and then names of speaker to whom you direct your questions, and of course your questions. At the end of the webinar, there will be a 30 minutes Q&A direct sessions, but hopefully we are on schedule. So the next speaker is the special guest. So all the speakers are special. So I will repeat this words. So we have Professor Kaljuna Dauka from Tokyo Institute of Technology. He is also a technical advisor of projects that we are working on from the last 2 years until 2023. He will be talking on our projects and how it relates to blue carbon policy. So Professor Dauka, time is yours.
Thank you.
15 minutes presentation. And I will ring my bell when you have reached the last 3 minutes. Thank you.
Oh. Okay. Thank you, Pak Novi, and good morning, all. I'm very happy to be here to have this very good opportunity to give you the very important message to you. And let me begin with this slide. This is the very basic information about project. The top panel shows the title of the project, Comprehensive Assessment and Conservation of the Blue Carbon Ecosystems, their services in the Coral Triangle. And project is the 5 years project. And this project is actually trilateral joint project between Indonesia, Philippines, and Japan, because these two countries, Indonesia and the Philippines, occupies a main part of the Coral Triangle. And this project is managed by the GST and JICA funding agencies through the SATES program. This slide shows the key questions of blue carbon. Yeah. In your project, Blue Cares, we are trying to answer properly to all these very basic, important questions. And in the final output of the project, we are trying to summarize all these responses to the questions in the form of the blue carbon strategy. The first question is very important: how to precisely assess blue carbon. For answering this question, we are trying to develop novel, new methodology. Unfortunately, due to the limited time, I have to skip the details. The second one is blue carbon has been well preserved or degraded. For properly answering, we have developed the methodology for nationwide monitoring and change detection, both with remote sensing application and CNS, that stands for Quantum Network System. Yeah? I will explain it later. Third one is, if degraded, what are causal relationships behind? The next one is, what will happen if no action will be taken? That is a matter of the future prediction. Therefore, we are developing an integrated model system as a future prediction. Sorry. And next question is how to properly conserve blue carbon. What is the best policy among the options? So for this subject, we will do scenario analysis with the model system to be developed. The last one is how do we link blue carbon with coastal ecosystem conservation efforts? For this, we are doing comprehensive ecosystem service assessment and others. Okay, I'll pick up only limited topics among these. First one is about nationwide mapping with remote sensing application. Recently, our partner group in the University of the Philippines, Diliman, have succeeded in developing the new methodologies that is quite accurate, rapid, and low cost. Yeah? That is quite useful. That is actually semi-automated mangrove extent mapping methodology, yeah? With the mangrove vegetation index, MVI, and some others, which this methodology was applied to Sentinel-2 images and others. That is a free image. So right panel shows the result of the nationwide mangrove extent mapping for the Philippines. Then we are moving forward to do nationwide mapping also for mangrove zonation, mangrove biomass mapping, and their change detection, okay, to find the historical change status. And we have to also try to detect the drivers causing such historical changes, like land use, land cover changes. And we have already set up the kind of working group for accelerating the similar attempts for Indonesia. The group consists of the Indonesia team, Philippine team, and Japan teams for remote sensing. But we have some limitations in this. How to validate the nationwide mapping results. We haven't yet have that kind of thing. And the more important thing is how to assess the below ground blue carbon. Yeah, actually, remote sensing cannot be applied to this. As you know, the majority of the blue carbon exists below ground parts, especially in the sediments. So therefore, obviously, we need to have another scheme for overcoming all these difficulties. That is a ground-based nationwide monitoring network. So in this background, we have put a lot of efforts for developing what we call core and network system, CNS. That is a platform for sustainable periodical nationwide monitoring of blue carbon ecosystems, including, of course, below ground parts. And monitoring results are critical for updating blue carbon strategy or policies as our adaptive management framework. Okay, this is the example at the Philippines. In the Philippines, we have the basic design consisting of 3 clusters, yeah, as indicated here. And what about Indonesia? Yeah, Indonesia is much, much bigger, yeah, than the Philippines. That is, a kind of the disadvantage, but we have advantage because you have the already existing nationwide networks like LIPI's network, KKP, and others. So therefore, we can properly link them for considering our CNS Indonesia, right? The panel below is the LIPI Korema project network. So we have also designed to set up a kind of large island-based cluster, like a Kalimantan cluster. And each cluster will have their local core institute. And the central core of the entire CNS is KKP Project Laboratory. We recently established the project laboratory in the Pasar Minggu, Jakarta, Indonesia. We held opening ceremony on the last January 20 this year. This is a main chemical laboratory, but aside from that, we also put the office room for accommodating the members, not only for the geochemical, ecology, but also some other groups like remote sensing, modeling, even socioeconomic, right? This is the main function of the laboratory. The first one is core institute in this CNS, in which we will do the laboratory analysis in the lab for the large number of the samples to be collected by CNS partner sites over the country. The second role is a key center or platform for integrated blue carbon and associated researchers in Indonesia. The last one is teaching center for students who are interested in conducting coastal and ocean-related studies for fostering next generation people. This slide shows some key points for innovating blue carbon studies. In the opening remarks, Mr. Chairman already referred to some of the keywords from the slides, like ecosystem-based assessment instead of the element-based assessment, flux plus stock-based assessment, local, sub-regional, regional, multi-scale assessment, and the future prediction analysis based on the development of the multi-scale integrated model system. And the last one is multiple ecosystem service assessment. Yeah, now this is the kind of the overall conceptual diagram indicating the structures of the multi-scale integrated model systems consisting of the local scale carbon dynamics models, seagrass, mangrove, coral models, and even the land model, watershed green carbon dynamics models, because we have to suppose the certain amount of the green carbon, aside from blue carbon, may be exported, discharged into the ocean. So the ocean is a kind of big pool of a mixture of green and blue carbon. Therefore, we are developing also the regional scale 3D models for that. Later on, Dr. Nakamura and Mr. Yoshikai will explain in some details about that. And this is actually the one of the project sites in Indonesia. Yeah, that is the below areas, including Delawan in the coastal. Yeah, so as you know, in the below areas, watershed areas, we have significant changes in the land use, land covers due to coal mining, oil farm developments, and others. Resultantly, we have the interannual increase in the turbidity in the coastal waters. So it may cause the declining trend in the optical condition for benthic habitats, especially the seagrasses and the corals. Yeah? We have already observed that kind of the negative linkage, yeah, groups. Therefore, our target is, of course, the coastal zone, blue carbon ecosystems. But appropriately understanding what is happening, we have to also look at the adjacent green carbon ecosystem part. Therefore, our target framework should be a kind of green-blue link, GB link. So very fortunately, in the terrestrial part, there is the ongoing programs, that is below forest carbon programs, PECA Happy, is that correct? Okay, so our idea is our project may contribute for developing GB Link program together with that existing program in the terrestrial part. So the title of this slide is Toward an Integrated Green and Blue Carbon Ecosystem Conservation Program Development. Yeah, that is one of the examples highlighting our efforts for contributing the blue carbon policy in this country. So this is the result, the example showing the historical changes of the land covers in that particular areas. The red part indicates the increased in the developed areas over this period. So yeah, this is actually the last slide of my presentation. Integration, linkages, networking, all those are keys to realize effective initiatives, policies, and actions for blue carbon ecosystem conservation and the restoration, and thereby for contributing to climate change mitigation. Thank you very much.
Thank you, Professor Nadaoka, for your insightful presentation, and it is also a perfect timing. Thank you. And next, we will have what we call as technical sessions. Yeah, there will be several speakers presenting their technical aspects on blue carbon's research. But before continuing, I would like to do a short polling. So we would like to know general information of the participants. So the first polling will be about you. We would like to know who you are. Okay, so let's let's bring up the first poll, please. All right, it's a simple one. Who are you? No right and wrong answer here. Okay. Please just click it and then click submit, right? So I will count in 5 and then I will close the poll and we will see the results. 1, 2, 3, 4, 5. Okay, I will stop the polling now. We can do it later if we have time. Okay, so most of the attendants are government officials. Okay, thank you. So then we'll move to the next first technical session speakers. So, Professor Nadaoka, could you please stop your sharing your share screen?
Okay, sorry.
Thank you. And the next one, we will have a talk on the mangrove mapping and how it relates to the coastal management in the Philippines. So we have Dr. Ariel Blanco. He is a professor in the University of the Philippines, and he specialized on geomatics. And he is the principal investigator of Blue Cares projects from the Philippine sides. So, Dr. Ariel Blanco, the floor is yours. Thank you. 10 minutes presentations, and I will ring the bell in on your last 3 minutes. Thank you.
Yeah, good morning, everyone. So I'll be sharing again my screen. I just checked some of my settings. So as mentioned by Dr. Noe, the title is Satellite-Based Mapping for Supporting Mangrove Management in the Philippines. So I will focus on what has transpired or what happened in the mapping of mangroves in the Philippines, but less on the second part, right? So much of the slides were prepared by Alvin Baloloy, who also primarily developed the mangrove vegetation index that was mentioned by Professor Onadoka. So the outline is shown here. So the historical and current mangrove extent in the Philippines, just to give some context, and then the variation in the extent maps, which maybe there are similar problems or issues encountered in Indonesia. And I will talk briefly on the mangrove vegetation index and also the challenge of blue carbon, which is the large-scale wild area mapping, which basically is needed for both Indonesia and the Philippines under the Blue Cares project. So here we see the images of the area in Samar. So this is an area where we are investigating also together with the Tokyo Institute of Technology. You can see here that the distribution extent have been changed because of the drivers such as conversion to aquaculture, but in this case, it's more on the effect of the super typhoon Haiyan or Yolanda, as we call it in the Philippines. And we have seen considerable recovery in some areas, but in most of the areas, we can see that some of the mangroves have remained nil. So in the Philippines, these mangrove extent have been documented locally very well by different groups, including Primavera and other ecologists, biologists in the Philippines. And different data, for example, those coming from remote sensing or the analysis of satellite and drone information, including those by Long and Geary. So the extent and historical and the current mangrove extents are actually can be done using, as you know, field survey approaches, wherein we do transects and the quadrat surveys, specifying the number of mangroves and so on. But in this presentation, I will focus on the remote sensing approach. So it can be from different platforms such as space, borne satellite, and airborne or aircraft, and also the unmanned aerial systems. But normally, depending on the application and target use, what we typically see are basically mapping of just the extent. But of course, under the Blue Cares project, we are extending it to estimation of above ground biomass, as well as the estimation of heights, estimation or mapping of the different species or genus or zonation, as had mentioned by Professor Nadaoka. And including also other elements such as the transition or the conversion from mangroves to ponds or fish ponds, and the different land cover and their corresponding changes. So different methodologies and workflows and field techniques and survey protocols, as well as different mapping assisted or image assisted mangrove mapping methods were developed and applied to different mangroves. Therefore, you will have a lot of variations and differences in terms of the aerial extent of these mangroves, so for the entire country or for different regions in the Philippines, as well as different accuracy. So as this in the data in the Philippines, the long-term data from the different years comes from the field monitoring, inventory, and mapping conducted by different groups, including the National Mapping and Resource Information Authority, plus the DNR, or the Department of Environment and Natural Resources, and the group of Dr. Primavera, Lawas, and so on. And then for the remote sensing applications, we will be seeing, for example, the data or estimates have been provided or extracted from different groups again. So you have DNR, you have Longingiri, which is global, and then you have the Global Forest Watch, as well as the different projects implemented by the University of the Philippines, especially, for example, the Field LiDAR to coastal resource mapping. And also recently, a few years back, so you have also coastal resource assessment being done by the National Mapping Agency of the Philippines, which is NAMRIA. So here we see the historical and current mangrove extent areas. So unlike Indonesia, so we have originally around maybe around 500,000 hectares. That's, for example, here in the graph, you can see from 1918, so around 450,000, and then because of the different factors, including the focus on the production of food in terms of the fish from aquaculture, fish ponds. So we have drastically reduced our mangrove cover to just approximately half of the original. So here we also see the different bars, vertical bars, indicating the whether the estimate is from field inventories or also from remote sensing. So from 1980s and onwards, so most of the data are coming from remote sensing. It's either from aerial surveys, photogrammetry, but more recently, of course, we have the remote sensing data from various sources. So here we see that the earlier years, so we have 450,000 down to 365,000 based on the estimates of Dr. Virgin Primavera. And then we also have the Department of Forest Development is already under, I think, the DNR, or the Forest Management Bureau, estimating a decline from 418 to 230,000 hectares. And then in the recent decades, we see that the estimates are coming from Longingiri, as well as the Global Mangrove Watch, as well as the data coming from the National Mapping Agency and the University of the Philippines. So this is what is shown here is the Longingiri map with an estimate of around 206 in 1,000 hectares in 2000. And in 2010, so it's around 240, 217 for the Global Forest Watch. And we also see here the estimate from the DNR. This is from 2003 with an estimate of 247,362 hectares. And here is the part of the Field LiDAR 2 project. So it's combining the use of LiDAR, but for the entire country, it's basically based on Landsat with validation from the LiDAR data that we have. So in 2015, the estimate was 208,220 hectares. And NAMRIA has its own estimate back in 2016 or around maybe 2017, so a value of 240. So we see here that even though we have, for example, very close years, 2015, 16, or even 17, we see a lot of variation, maybe in the order of 10% or even 20%, 15% difference. And much of these variations are actually coming from the difference in the mapping approach, of course, field versus remote sensing based, or also from the difference in the satellite images utilized. So here we see that in Landsat with 30-meter resolution, the Sentinel with 10-meter resolution, and PlanetScope with 3-meter resolution. And from this alone, we can see that we can have varying levels of accuracy as well as varying levels of the estimates in terms of the aerial extent. So there are also differences in the field inventory protocols and also change analysis for if you are producing estimates every year or every other year or so. Then you focus on some of the changes and then update the inventory. But this usually is not applied at the national scale. And there will be also errors or variations coming from the recomputation of area based on the previous secondary data. For a case in point is the application of a fixed annual rate to interpolate between the estimate text. And if we do mangrove classifications in remote sensing, then there will be also variations in terms of the degree of error in selecting ROIs, the different misclassifications resulting from these, as well as the performance of the different algorithms that is used. And if we use a global scale data set, then a single methodology applied to globally to all regions may yield or usually yield different accuracy depending on whether you have not enough or not enough data coming from those regions. So here we see example delineations, the yellow polygons representing mangroves. So this is a false color composite image with red being the mangrove. And we can see here that the delineation are some B and C are fairly similar, but A is slightly more generalized. So this one is from Longiri, that's the 30-meter, and then 2018, that was Sentinel from the IMBLUE-SEACAM Blue Cares project, and then the Landsat, the 30-meter resolution from the Global Mangrove Watch. And we can see these distinct differences, including in that would be included or not included in the area. But we can see here that the IMBLUE-SEACAM Blue Cares result is fairly accurate, or the most accurate of this in terms of this visual. So therefore, satellite resolution is one of the critical parts. So here we see another example for the case of the field LiDAR to POSMAP, and then the Global Mangrove Watch for 2016 and 2015. So the Blue Cares project, the IMBLUE-SEACAM program, which is the counterpart program, developed this mangrove vegetation index, which is the SWIR minus green reflectance divided by the NIR minus green. And this is fairly easy to use and implemented using Google Earth Engine as well as the IDL script. And we can see here that we can highlight the dominance as the index highlights the mangroves in contrast to other vegetation or land cover purpose classes. So this is an example of the MBI. So for different applications in Japan and in Philippines and even Indonesia. And then in the paper, we have also added sites from the different portions of the globe. And for the Philippines, we have applied this using the MBI mapper, which is a Google Engine-based application. So it will be easier for us to do this for earlier years or do this also for the current year, 2020, considering if we would like to detect cuttings or deforestation in some areas. As shown by Professor Nadooka, so based on this MVI approach using Sentinel-2, so we have come up with an updated total mangrove extent in the Philippines with an area of 231,359 hectares. And if we compare this with the earlier estimates, for example, the most recent one will be for Longiri, which is 222,000 hectares. So more details of this MVI can be found in this paper. So the development and application of Green Mangrove Vegetation Index, or MVI, for rapid and accurate mapping application. So recently published just this August. And then the highlights will be this utilizes 3 reflectance bands, green NIR and the SWIR1 band of Sentinel-2. So the index is accurate to around 92% also, and it measures greenness and the moisture information. And we correlated this with the Sentinel-2 physical input products such as LAI, top of the canopy, chlorophyll, and so on. And we have developed the IDL-based and GE-based MVI automated mapping. So we have been using also MVI for several applications in the Philippines. So this is including the investigation on the recovery of Haiyan mangroves or Haiyan or Yolanda-affected mangroves in Eastern Samar. So we can see here 2013 and then almost totally wiped out in 2013 in these 2 towns of Lawan and Balangiga in Eastern Samar. And then we can see recovery in certain places, but it hasn't fully recovered, of course, the lost mangroves back in 2013. So this is a thesis which will be presented and defended this coming Friday by 2 of my students. So what we are doing or challenge in our challenge in Blue Cares is to perform the large-scale wide area mapping not only for this extent, but of course, to extend it to the blue carbon estimation above ground biomass, even below ground, and even the soil. So for this large-scale wide area mapping, we would like to have it applied for the entire Philippines. I think for Indonesia, it will be more challenging for the entire, say, Indonesia. And it will be of a larger scale, utilizing relatively high spatial resolution, so preferably the 10-meter resolution, because that is the highest, which is free. And then we have a higher temporal. Maybe we can do this almost every year or every 2 years and so on. But of course, it can be done more frequently depending on the disturbances before and after the typhoon. So for this large-scale wide area mapping, so we have done the extent, the height, and the DBAs. We are working on these plus the density, and we have also developed initial methodology on the zonation. So the general zonation patterns of the different mangroves in the Philippines. So this is what is shown in the figure to the right, wherein you can see that based on the different factors, including the biophysical estimates from Sentinel-2, you can detect the zonation patterns. And of course, this has to be validated or confirmed using field surveys, whether what composition or what species really comprises this zone 1, zone 2, zone 3, and other zones. So we are also collecting soil and sediment data, and the changes and variability will also be examined. So all of this, given the extent of work, we have to tap really to the core and network system, as highlighted or emphasized by Professor Nadolfo. So that's all for my presentation. So thank you very much.
Thank you very much, Dr. Ariel Blanco, for the presentations on the mangrove remote sensing. And we are now trying to apply the MVI for updating Indonesian mangrove. So we are now still discussing with the data custodian for Indonesian mangrove, which is the Ministry of Environment and Forestry, for the possibility of applying this new algorithm for updating Indonesian mangrove area. So the next one, thank you, Dr. Blanco, again. The next one, we will have some insights on different key coastal ecosystem, which is seagrass. And we now have Dr. Matt van der Cliff. He is a director of Indian Ocean Rim Associations, or IORA, for Blue Carbon Hub. And he's affiliated with CSIRO Ocean and Atmosphere Australia. And he will be talking on seagrass blue carbon. So let's welcome Dr. Matt van der Cliff. Matt.
Thank you, Novi. Yes, moving from mangroves to seagrasses. Some of the challenges that we face with seagrasses are the same as those that we've just heard from Professor Nadolfo and Dr. Blanco. Some are different. The seagrasses live underwater, and being underwater provide some challenges because we have to look through the water if we're measuring from space, and we have to get in the water if we're doing the validation. So let's start with thinking about what are seagrasses. Well, you're probably familiar with, if not seagrass themselves, then at least the type of plants they are. They're monocots, and there's lots of monocots that grow all around us, things like regular grass, but also rice, sugarcane, even bamboo. There's about 60 or so species of seagrass in the world that really encompass a range of shapes and sizes, and that really determines the role they play in the ecosystem. For example, ones that are small tend to be preferred by dugongs, ones that are sort of moderate sized, good fish habitat or turtle food. Larger ones with lots of woody below ground matter are important for climate change for reasons we'll come to. They're found everywhere except Antarctica, usually in shallow coastal water, but also in the high seas, in shallow areas like the Mascarene Plateau in the Indian Ocean. They're most diverse in the Indo-Pacific, especially in the area around Indonesia. So we've heard some estimates of how much seagrass there is in Indonesia. We heard some 3 million hectares before. Well, how much is there? What do we know about it? There's, like we've heard with mangroves just now, there's varying estimates. The World Conservation Monitoring Centre has seagrass layers that are represented on this picture that show around 18,000 kilometres, where the World Seagrass Atlas says there's around 30,000 square kilometres. But we don't know where that particular data comes from. And when we look at the World Conservation Monitoring Centre data, we see that it's actually not that great. It's mostly blobs drawn on a map, but not actually validated. So why do we need to know? We heard a little bit about that from the excellent talk by Dr. Anwar before, where in order to get a national stock, we need to know the area of the ecosystem we're interested in, as well as the mass of carbon per unit area. And by a simple process of multiplication, we can have the sort of approximate national stock. And that's a starting point, an important starting point we need for things like our greenhouse gas inventories. Now, I think Dr. Anwar mentioned that seagrass is less relevant for REDD+, because they're not forests, but they're very relevant for nationally determined contributions and the greenhouse gas inventories, and those are things that we focus on. So how do we get to our estimates of area of seagrass? Well, a little bit like RL just mentioned, we try and map it from space, but it's not that simple. As I've mentioned, there's lots of things to consider. Not only are you trying to look through the cloud and the atmosphere, but you're also trying to look through the water. So the water properties matter. And here is an image which is similar to the one that was shown earlier, which shows you also the type of platform matters. Everything from Landsat 8, with a relatively coarse resolution of 30 meters, but one that goes back for several decades, all the way through to some pretty high resolution data, but that don't go back very far at all. So getting estimates of change is more difficult. I took that figure from this report. I'll leave it up just for a few seconds, take a snapshot of it, but it's also there in the PowerPoint, which is in the materials. Another figure that I took from this report is shown here, which shows the difference that can make. This particular example is from Greece, and it shows in the middle that World Conservation Monitoring Centre estimate. That's the one that I showed before for Indonesia, says 18,000 square kilometres. Well, they found that when they used higher resolution mapping for this area of Greece, that they got 4 or more times the amount of seagrass from that method. So it really does matter. And so it takes us back to the question of how much seagrass is there in Indonesia? Well, that estimate of 18,000 square kilometres is likely to be wrong. It's likely to be an underestimate. The estimate of 30,000 square kilometres might be closer, but we don't really know. The true answer is it's probably a lot more. The more we look, the better we get at getting high resolution data, and looking through the water column, the better the estimates that we get. But we can't stop there. Those maps also need validation. We need to get in the field. For seagrass, that usually means getting in the water and ask questions like, well, is there seagrass there? Is the satellite data correct? Or is our interpretation of the satellite data correct? What species are there? How much in terms of, the percentage cover, the amount of material, the mass? So I won't go into that in more detail. I will simply refer you to this report led by some researchers from LIPI and in Indonesia, of course, and other organizations. And that has as much detail as you could want on how to go about doing field surveys and validation of seagrass and monitoring. But of course, to get estimates of seagrass from satellites, we also need to have the reflectance spectra. And this is there to remind me to say we actually don't have very many good data for tropical species, especially the species that you find throughout Indonesia. So that is a real data gap, and we need to start addressing that. So the more data we get for looking through for the water column properties in Indonesia and the reflectance of the seagrass species we find in Indonesia, the better our maps are going to be. So that's a call for all the researchers out there. What about loss? We can measure what's there now, but we know that what's there now is different from what used to be there. There's an estimate a few years ago now of seagrass loss around the world, and that estimate essentially didn't have anything from Southeast Asia. I think it's time for us to review this gap. We know that there's been seagrass loss in Southeast Asia, including in Indonesia. And my suggestion is that we get some knowledgeable people together and we start reviewing what we do know. Perhaps we can collect some new data, but I suspect there is more data out there that we can use. And if we do that, we can start thinking about restoring seagrass. I mentioned the biomass of seagrass, well, between the biomass in the seagrass, especially below ground, and in the soil. If we start restoring seagrass, there is the potential, and I stress this is potential, this is not realized, of getting more than 10 million tons of CO2 sequestered each year. That's a lot. It's a big ask. Can we do it? Well, one study from Western Australia suggests that we can. There was a lot of seagrass in the 70s that was lost in the 70s and 80s. In 2001, in Oyster Harbour on the south coast of Western Australia, there was some seagrass was replanted. If you see on the left, the red squares. 10 years later, those replanted seagrass had grown back, and when the carbon was measured in the replanted seagrass, they found that the recovered seagrass had regained its sequestration capacity. So within 2 decades, the seagrass had regained its ability to store carbon below the soil. And of course, if we do that, there's so many more benefits that we can get from that. It's more than just about carbon. There's also benefits to livelihoods. There's a lot of fish in those seagrass, a lot of juvenile fish that provide benefits through fisheries, for example. There's the coastal protection benefits. Seagrass don't tend to dampen waves too much, but they do dampen currents and tend to settle out the particles in those currents, as well as simply the biodiversity. So I'm going to stop there. That was a very high-level, quick overview. If you go to this link here, the Blue Carbon Hub website, you can get the documents that I've highlighted in this report and a lot more information. And I look forward to your questions and look forward to having many more productive research collaborations with Indonesian colleagues and others. Thank you, Novi.
Perfect. Thank you, Matt. Very nice presentations and perfect timing too. And so now under the technical sessions, we already have 2 speakers talking about mangrove mapping using remote sensing by Professor Ariel Blanco and by Dr. Matt van der Cliff from CSIRO talking on seagrass. So for the next 3 speakers, we will have modeling sessions. Yeah. So we will have hydrodynamics modeling as well as biogeochemistry modeling and also ecosystems modeling as well. So, but before moving forward, please type in your questions in the Q&A chat box, and please, all the speakers, take your time to keep monitoring the Q&A checkbox. If there are questions directed to you, and you can type in directly to answer them. So next we will have Dr. Takashi Nakamura from Tokyo Institute of Technology. He is an associate professor of Tokyo TATEC. That's the acronym for Tokyo Institute of Technology. And he will be sharing on his expert and knowledge on the integrated system for revealing fate of green and blue carbon. So it is like an integrated ecosystem of the forest ecosystem and coastal ecosystem. So Dr. Nakamura, please take the floor.
Yeah, terima kasih to Pak Novi for introducing me. So I will share my slide now. Okay, sorry. So again, nama saya Takashi Nakamura, Associate Professor in Tokyo Institute of Technology, Senam, Buldum, Degan, Anda. That's all for my bahasa. So today's my talk is thank you. Today's my talk is an integrated modeling system for revealing fate. Just changing mute. So as you know, that blue carbon is one of the key keyword. And blue carbon is defined as a marine green carbon, and green carbon is defined as a carbon that plants have assimilated via photosynthesis and incorporated into organic matter. So just we observing a mangrove, blue carbon, mangrove seagrass. So here, that part is assigned as a blue carbon, and we measuring a blue carbon, the above ground biomass. And also here is also the blue carbon we are counting, and below ground or sediment, sediment organic carbon is counting as a blue carbon. So we can. It's also still have a difficulty to measuring the technical issue, but we can measuring as a blue carbon. But how about this part? Sometimes litter is flow to the outer system, and this is also the blue carbon. Should be blue carbon, but we are usually neglecting. But what happened after exported to the outer ocean, such kind of blue carbon? It's firstly exported as a DOC, dissolved organic carbon part, or particulate organic carbon. And many of this part will be decomposed and changed to the CO2 and degassed and returned to the atmosphere. But some part will be remained as a refractory DOC, dissolved organic carbon, or some part of the POC, particulate organic carbon, will sinking and deposit to the terrestrial transitional areas, or that one may transport it more deeper portion, and again to the changing to the refractory DOC, or changing to the DIC. Decompose the DIC, but this part will be storing for long term. So storing long time for example, a few 100 years or 1,000 years, and part of this POC should be sinking to as a bottom sediment. So from this point of view, carbon sequestration potential by coastal ecosystem might be underestimated. So of course we are just now counting the seagrass, blue carbon as a above ground biomass or below ground biomass or sediment, organic carbon incorporating in the sediment. But we need better to include this part as a blue carbon. And yeah, so that usually we may underestimating for the potential of the carbon sequestration by blue carbon ecosystem. So for estimating the proper sequestration potential and tracing carbon produced by coastal ecosystem at its fate should be elucidated. So for understanding and chasing the carbon, so we are developing the low trophic ecosystem model, including the isotope modules, carbon isotope modules. This is an overview of this model. And this low trophic ecosystem model includes water quality, DO, DIC, alkalinity, ammonium, and nitrate, and phosphate. And also material cycles in the sediment was developed, and it's coupled with the ocean circulation model. And this model includes this part, coarse particulate organic matter, assuming as a leaf litter, such as a mangrove leaf litter or a seagrass leaf litter. And also the or terrestrial green carbons. And this, and also not only the material, but also the carbon isotope module is also incorporating. And this is possible to trace carbon from a certain source. So let's close up this part, pelagic part. So here is a coastal particulate organic matter, coarse particulate organic matter, assuming mangrove or litter. The some part will be eaten by zooplankton or some part decomposed. This is a floating ability, but some after decomposed to the detritus part, it will be sinking to the deeper portion. And some part will be decomposed to the DIC, dissolved inorganic carbon. This is one of the CO2 dissolved in dissolved ocean and return to the air, or this one again to the fixed by phytoplankton, and again grazing or producing DOC some part. So yeah, such kind of material cycle was precisely incorporating, and also carbon-13 modules, also including and tracing the carbon to which part is transported, which carbon transported, how many carbon transported to the, for example, to the plankton or detritus part. So, and we are prior developing the hydrodynamic model in the Ishigaki Island or Sekisei Lagoon or Yaeyama regions. So this one, this hydrodynamic model is multi-nested 3D circulation model for Yaeyama region, and used based on the coupled ocean atmosphere wave sediment transport modeling system. It's called the coast modeling system. And the boundary and the initial condition is used the global HYCOM data set, and that one is nested downscaling to for keeping high resolution from the global HYCOM output to Yaeyama 1 grid. Its grid size is 1.5 kilometer, and again nesting to the more high resolution to Yaeyama 2 computational grid. It's called the grid side is 300 meter. So, and then the low trophic ecosystem model is incorporating in the hydrodynamic model. We can simulate the tracing the fate of the particulate organic carbon, coarse particulate organic carbon from the here is a mangrove zone exists here. This it's called the Nagura Bay, and from here the mangrove leaf litter is exposed to the open ocean. But yeah, difficult to chasing from the, for example, maybe some of the coarse particulate organic matter will decompose and changing detritus form, but detritus form, as you can see, is affecting from the, for example, phytoplankton production or zooplankton or some other, and maybe this part will be decomposed to the dissolved inorganic carbon form, but only the concentration base analysis, we are difficult to chase the how many organic carbon coming from the mangrove leaf litter will be transported to offshore. So yeah, that's why we are incorporating the carbon tracing using the carbon-13 tracer. But in this case, we are not incorporating the isotope fractionation function because we are just want to know that the carbon transport and changing form to the coarse particulate organic carbon to detritus type or other DIC forms. So yeah, from this using this trace element, we can clearly know how many organic carbon is converted to the detritus part or refractory DOC or decomposed as a DIC or incorporating to the phytoplankton from the DIC originated from the mangrove will incorporate fixed as a phytoplankton or eaten by zooplankton. Such kind of material paths were precisely reproduced from using this tracing simulation. And now, Professor Nadaoka is already mentioned in this showing on in the slide. But this part, local scale blue carbon dynamics model, will be introduced by Mr. Yoshikai. And this part, we are now developing the multi-scale, multi-nested 3D ocean circulation model. And also watershed green carbon dynamics model. If time is okay, I will introduce this part. So firstly, for understanding the terrestrial runoff with green carbon based on SWAT Plus, which is the latest version of the widely used watershed model, SWAT, Soil and Water Assessment Tools, is one of the open source software. We incorporating green carbon discharge process and modified SWAT Plus. It's called SWAT Plus C. And this is one example of the this is a time series of DOC and POC discharge from the Todoroki, one of the river watershed computed by SWAT Plus C. And now the SWAT Plus C was coupled with a 3D ocean circulation model for estimating terrestrial impact on the coastal ecosystem and tracing the fate of the green carbon. And also human impact. This is this model including the land use change and land use and human impact will be how to affecting the human impact to the coastal ecosystem will be estimate from using this coupled model with SWAT Plus C and hydrodynamic model. And now we are trying to developing the coral ocean circulation model, multi-nested 3D ocean circulation model, including the coral triangle region. So, and we are now downscaling to Makassar Strait region like this. Then the one of our target study site is Derawan Berau region is here. And again, downscaling the Berau Derawan region. And now we are starting to develop this ocean circulation model and try to incorporating the ability for the ecosystem model. And also this is one of the example of the just incorporating the coupled of the coral triangle model with ecosystem model. This is my student Amri computing this output. Of course, parameter tuning and model validation are still needed, but the CO2 system parameter were reasonably produced. For example, sea surface total alkalinity map and sea surface DIC and PCO2 map. And this is observed PCO2. Still have some discrepancy, but we will now trying to tune the more precise modeling. And this is the last slide. The summary I will skip, but future works, continuing to develop an integrated modeling system and apply to the system to coral triangle region and the Belau-Delavan region for understanding overall figure of the blue carbon sequestration potential and its dynamics in these regions. Okay, terima kasih. Thank you very much for kind attention.
Thank you, Dr. Takashi Nakamura, for the presentations on the integrated green and blue carbon modeling. Very insightful presentations. And yes, we are under the SATREPS Blue Cares. We are trying to implement this to couple, or to not couple, but to advise how the terrestrial spatial planning needs to be considered, need also to consider the marine spatial planning. Okay, thank you once again. And next one, we will have speakers from my own center. He's in fact my colleague, Dr. Dwi Yoga Nugraha, and he's a research scientist at Marine Research Center, Agency for Marine and Fisheries Research, Ministry of Marine Affairs and Fisheries, Indonesia. And he will be sharing on his expert and knowledge on the biochemistry modeling, particularly in East Kalimantan area, Derawan Islands. Dr. Yoga, please take the floor. Oh.
Yeah, wait, I have some problems with the connection. Just wait 1 minute.
Okay, please take your time.
Yeah, can you see the presentation? Novi?
We do. Yes, we do.
Okay.
Perfect.
Okay, good morning, everybody. My name is Dwi Yoga Nugroho. I'm one of the member in SATREPS Blue Cares Geometric and Modeling team. So I'm going to talk about our preliminary modeling results about in the Derawan Islands for the biogeochemistry and also the coupled biogeochemistry and physical models. So first, I would like to show you that our goals, our goals in the team is to develop tools to support the SATREPS Blue Cares using numerical models. So we already developed from last year the 112-degree resolutions. It's another version from the Indonesian operational oceanography model, call it the INDOSIL 12-degree resolutions. And the model works good. And this year we tried to refine the model to 3-kilometer resolutions or 136-degree resolutions. And we plan to deploy also some instruments in the river and in offshore, but fortunately because of the COVID-19 pandemic, we cannot do that. But we still we're still working on the improving the forcing input for the from the global services. It's like a global marine Copernicus services. And then we migrate the last year we used the old version of the models, we call it the NEMO models, and now we migrate to the recent version of the models, and as well as the recent version of the ecosystem model, we call it FISCAS. And we hope that next year we have our model already works and operational to support the SATRAPS project. Okay, this is our study area, and the Derawan Islands is located in the Sulawesi Sea. It is just like a semi-enclosed basin surrounded by the Sulu Strait, Sangihe Islands, and then it's very interesting to see the oceanographic feature that influence the Derawan Islands. And this is our zoom image of the Derawan Islands. So you can see that there is a Berau River here, Berau River, and then it supports some fresh water to the ocean, and just like a wall, some coral reef islands here just in the eastern part of the Berau River, and then we can find in the eastern part is the Sulawesi Sea. What is interesting in this two model in Derawan Islands is that the inputs of the baroclinic input from the South China and North Pacific and Makassar Strait. So I collect the information, the transport information, the baroclinic transfer from the previous paper. That it said that there are some transport in the thermocline, mainly from the North Pacific input with the characteristic in the strong salinity in the thermocline, and then we have also some tidal dissipation in the Sulu and Sangihe Strait. So all the water mass will going out to Makassar Strait, and I assume our first guess that all the oceanographic dynamics in the Sulawesi Seas will bring influence to the Derawan Islands. So this is the bathymetry of the Derawan Islands. It's very shallow in front of the river mouth. It's about 0 to 50 meters, maybe 0 to 100 meters. And there is an island, the coral reef belt or coral reef islands in front of the river. So the currents will maybe there are some dynamics in the estuary. We call it the tropical continental shelf semi-shielded by coral reef. That's the research from my colleague, the Aitaria 2018. So the dynamics between the Berau River and the Derawan Islands is very, very interesting and is unique. But in the eastern part of the Maratua and the Derawan Islands, we also have the island is facing the Sulawesi Seas with the steep topographic gradient up to 6,000 meters after the shallow water. And this is I have this data from the SATRAPS meeting maybe last year. That this is the preliminary results from the water quality team when we conducted the survey last year. So mainly the temperature, salinity, and oxygen, as well as chlorophyll, is high in the river mouth, but is also in the but the survey is only near the coast and in the river mouths. But we don't have any information in the open seas in the Sulawesi Seas. And then how to study how to see if the dynamic of Sulawesi Seas give impact to Derawan Islands, or we just need to create the model just in the Derawan Islands, or we need to create a larger domain model. And then we conduct a regional numerical model. I'm using the NEMO. NEMO is a Ocean General Circulation model from the European Union. And for the ecosystem model, I'm using the PISCOS because I'm familiar with these two models. So I'm using the same grid as the previous Indonesian oceanography model. So the grid, this is the domain with cover all the Indonesian seas from Andaman Seas to the east part of Papua. Their grid is 112 degree resolutions, and then the transport, the thermocline transport in the right side of the model. So what we have done since last year is we try to develop, or we try to make some another different configuration with the previous model. So the previous model called the Indesos, it's based on NEMO 2.3. It covers all the Indonesian seas in 112-degree resolutions, and we try to develop another models. We call it the SATREPS. The difference is the forcing. In Indonesian model, the forcing is the tides is the tidal energy is generated by the barotropic tides, and also the tidal mixing parameterization in order to generate the vertical mixing. But in SATREPS, we don't use the tidal mixing parameterization. And bathymetry, we also changed the bathymetry, but the simulation, because this is still ongoing works, we just finished only 3 years for the SATREPS model. And the initial condition, we get the initial condition from the Indonesian model. And all the forcing, another configuration for the vertical mixing is the same with the previous model. And for the ecosystem model, we migrate from the PISCAS version 1, that's in the Indonesian model, to the PISCAS version 2. And we have, actually, we have 24 variables of biogeochemistry in this model. And the inputs is, we got the inputs from the World Ocean Atlas for climatology, for nitrate, phosphate, silica, oxygen, the IC, and alkalinity. And also we got, this is the table under here is the biogeochemical inputs. You can see the inputs to do the model. So what is the remote forcing that might give influence to dynamics of the Derawan Islands? And then for this research, we conduct 2 simulations, because we have here, this is the study from Naga in India 2015 in the Sulawesi Seas, that there's a strong, that Sulawesi Sea is a region of the propagation of the internal tides. So the internal tides is mainly generated from the Sulu and the Sangihe, and then it's propagated to the Sulawesi Seas. And then also in the Derawan Islands, you can see the lower figure here. That is a strong generation and also dissipation tidal energy in the Derawan Islands. So it's very interesting. And what about our model? We here is the results of the model. We plot the 1,000 depth at the depth of 1,000 meters. We plot the instantaneous model vertical velocity, and we compare with the satellite MODIS on the same dates. And we can see some signal of propagation of the internal tides. So the model has already validated. Here we validate our model with the assimilated tidal data from the FAS 2014. We get a good agreement for the semi-major axis velocity, as well as the barotropic energy flux from the model and the assimilated tidal model. Also, we validate the model for the baroclinics validations. This is the works from the Alford 2015 that he put some many instruments to see the baroclinic flux in the Luzon Strait, and then we use this data to validate our model. And the model is good, even though the model is only 112-degree resolution, but it's close to the works of Alford in 2015. So this isopical displacement from our models in depth of 50 meters, we get the propagations of some internal tides up to 10 meters that generate from the Sulu and the Sangihe, and some of the waves will going through the Derawan Island. So I think we have remote forcing from the internal tide that must be taken into account in the model. So this is our preliminary research. We make some simulation with tides and without tides. So with tides the model is forcing with the barotropic tides, and without tides the model is just forcing. It's just forced by with the baroclinic forcing. So the results here, we can see the cooling effect of the tides in the model. So if you compare with the observation from Ocean Atlas, that there's not so many information in the Ocean Atlas. I think either our model we need to calibrate, or maybe the World Ocean Atlas is not adequate enough to create the sea surface temperature in this area. So the cooling process is, we can see here that there's a minus 0.4 degrees Celsius, the cooling process, because of the tides. And the tides is important in this region. Also, we can see this is the chlorophyll. The chlorophyll, the difference with if the model is forced with tides and without tides, and then this is the difference. There's a difference is about 0.5. This is the units in upper. I cannot see the units here. So maybe I assume that there is some transport of the chlorophyll from the Sulu Strait to the Derawan Islands. It needs more research about that. Is the Derawan Islands receive the chlorophyll also from the forcing from the remote forcing or not? And also I've made some plots for the oxygen. So this is the plot of the oxygens from the two simulation, and then this is the difference for the oxygen. We can see here that there's the concentrations in the Sulu Strait and is higher when we add tides, and then along the coastline of the Sulawesi and Kalimantan coastline, we have more concentration of the oxygen. Is it the Derawan Islands receive another? There is some circulation of biogeochemistry transport in this region or not? We still try to make some research in this problem. So this all our results, and then we have some discussion that our model we already built our model, and we think that our model is good, especially in the tidal energy. And then we converted our Indonesian ocean model from the old OGCM NEMO model to the latest NEMO model to support the future modeling works, because we want to refine the horizontal resolutions in the area. And then we guess that the Derawan Islands receive some remote forcing for the biogeochemistry from Sulu Strait, Sangihe Strait, that might give influence to the biogeochemistry of Derawan Islands. So they integrated of just like the previous presentation, that there is a nutrients input, the biochemistry input from the Derawan, from the Berau rivers, and it will disperse and it will diffuse in the transported in the Derawan Islands, and it might also there is some potential vertical transfer from upper thermocline in Sulawesi to Derawan Islands. So another important thing is the effect of the vertical tidal mixing to biogeochemistry cycle is still a big question, and especially in Indonesian seas. So we hope that we can deploy some instruments in the Derawan Islands to see the mixings that is related to the biochemistry. And then we need a further study and instead of the data measurements, especially to the upwelling of nutrients from the Sulawesi Sea to the Derawan Islands. So that's all my quick presentation for this morning. Thank you very much, Pak Novi.
Thank you, Yoga. And we will have the last presenter under the theme of modeling for these technical sessions. And the next presenter is Mr. Masaya Yoshikai. He's a project researcher from Tokyo Institute of Technology, and he will be talking on the blue carbon dynamics model, both for mangrove and seagrass. Yoshika-san, time is yours.
Thank you, Nobi-san. Can you see my slide, Nobi?
Yes, we do. Perfect, thank you.
So, good morning, everybody. I'm Masaya Yoshikai from Tokyo Institute of Technology, and today I'm going to share with you some research output on mangrove and seagrass biomass dynamics and some future plan for development of blue carbon dynamics model. So firstly, I would like to talk about seagrass part, and this is schematics of blue carbon dynamics in seagrass beds, and some blue carbon dynamic model that we are planning to develop as introduced by Professor Nataoka. So we are considering two main inputs for soil organic matter. One of them is internal inputs through root turnover, and another is external input through deposition of organic matters. And they also resuspended or transported horizontally. And this process is controlled by hydrodynamics. And hydrodynamics in seagrass beds is affected by drag effects of seagrass leaves. And seagrass leaves also contribute to floating organic matter by detaching leaves. And also they promote organic matter deposition through trapping effects. So all these processes are connected for blue carbon dynamics, and we have to couple each model closely. And this is actually not completed yet, and we are still developing the model. But so today I would like to focus on this one, hydrodynamic biogeochemical model and seagrass growth model. And this is a study site for model application, Bolinao in the Philippines. And there are two distinct areas in the area here. The one of them is mariculture area, and another is seagrass bed. And in mariculture area, there is intensive mariculture activities, and excessive fish feeding has become one of the serious environmental laws here. On the other hand, in seagrass bed, we can see abundant seagrass beds. However, the water quality in this area has degraded, and due to reduced light, primarily due to increased phytoplankton, seagrass bed within or near the mariculture area have declined. And this figure shows a comparison of species richness between 1995 and 2012. And you can see the decreases in species richness in the seagrass beds nearby mariculture areas. And also here, there were seagrasses in 1995, but there's no more seagrasses today. So to assess the impacts of mariculture activities on seagrass beds, firstly, we developed hydrodynamic biogeochemical model. And these are the results of 1 year averaged water quality of dissolved inorganic nitrogen
chlorophyll A, light attenuation coefficient, and relative light intensity. And we see the high nutrient concentrations and also high phytoplankton concentrations. And then light attenuation in the mariculture area is high, meaning the water is turbid. And also there are some special extents to seagrass beds nearby mariculture areas coming from this area. So based on these results, we simulated seagrass growth. And these are the results of seagrass growth model for Thalassia hemplici and Enhalus acroides. And then we compared this above ground biomass distribution with field data collected in the seagrass beds at around maybe 20 or 30 stations. And as you can see, the simulated above ground biomass agreed with field data well for both species. So I would conclude that seagrass growth has been successfully modeled. Yeah, and next I would like to move to mangrove part. And this one shows the schematics of blue carbon dynamics in mangroves. And we think the processes controlling blue carbon dynamics in mangroves is very similar to the case for seagrasses. But one difference is presence of very complex above ground roots of mangroves. So they may greatly affect hydrodynamics and ultimately soil organic matter. And drug trapping efficiency production turnover rates, which affect soil organic matter, depend on species and tree size density. So it is important to properly model mangrove biomass dynamics. And also because the above ground root greatly affect hydrodynamics, it is also important to model above ground root morphology. So I will talk about these two parts, biomass dynamics and above ground root morphology. So because mangroves grow in intertidal zone, their growth is under salt stress. And mangroves usually form species zonation from seaward to landward. And the soil salinity is considered as one of the dominant factors in this species zonation. And this figure shows the effects of high soil salinity on nutrient uptake rate and carbon uptake rate. So negative water pressure potential in soil by osmotic effects lowers plant water uptake rate. And because of this, nutrient uptake rate also lowers. And plants try to not lose water by regulating transpiration through closing stomatal conductance. And because stomata is a pathway both for water and carbon, this leads to decrease in photosynthesis rate. So modeling this kind of mangrove responses to soil salinity is important for understanding the mangrove biodynamics. Therefore, we have developed this kind of model for mangrove growth model to assess the effects of soil salinity and also nutrient concentration in pore water on biomass increment, and then ultimately changes in tree morphology. And this model was implemented in SaveDZ-VM, which was developed for simulating terrestrial forest ecosystem. And this model can compute light and space computation with neighbor trees. So after implementing this model to SaveDZ-VM, analysis of forest scale mangrove biomass dynamics can be achieved. And I'd like to show some preliminary results of simulation. We conducted a mangrove dynamics simulation for Fukido mangrove in Ishigaki Island in Japan. And we tested mangrove simulation under soil salinity with 20 per mil, and soil salinity is 30 per mil. And we compared simulated above ground biomass with field data. And you see the overall trend of above ground biomass and species composition along a soil salinity gradient was reasonably reproduced. So actually, we are trying to improve the model for more realistic simulation. But other than soil salinity gradient, we are also trying to improve the model for simulating mangrove dynamics under different climate conditions and typhoon frequency and so on for application of the model to various mangrove forests in Coral Triangle region. And then blue carbon dynamics model for mangroves requires a coupling of mangrove dynamics model and hydrodynamic model. And for doing that, drag effects of complex structure of mangrove above ground roots on flow and deposition, resuspension, and sedimentation organic matter needs to be taken into account. So therefore, we try to develop a simple but accurate empirical model for predicting the vertical profile of above ground root projected area, which is needed for quantification of mangrove drag. So this is a typical view of mangrove above ground roots of rhizosphere trees. And we see very complex root structures. And it is very difficult to measure the projected area in the field. But we found that there is a very strong relationship of above ground root projected area with tree diameter. So this relationship is actually allometric relation, regarded as allometric relationship. And based on this relationship, we developed an empirical model for above ground morphology. And as you can see, the modeled projected area agreed with field data very accurately. So we think this model is useful when coupling mangrove dynamics model and hydrodynamic model. Yeah, so these are the future works for development of blue carbon dynamics model. Firstly, we have to implement vegetation drag in hydrodynamic model, and then we have to develop soil organic matter dynamics model. And in the model, we have to consider production turnover, decomposition of mangrove fine roots and seagrass roots, and also advection, deposition, resuspension of sediment and organic matter in mangroves and seagrass beds. And these are very challenging and actually a lot of works, but we are trying to achieve the model development. So thank you very much. Terima kasih.
Thank you, Yoshikawa-san, on the presentations. So we have already completed the modeling subjects under the technical sessions from Dr. Nakamura, Dr. Yoga Nugraha, and from Yoshikawa-san. So the last two presentations, so we designed the last two presentations to be more practical, more understandable, hopefully. So, and the next one is from Dr. Kazuo Hirose. He's a director of international cooperations of Japan Space System. So I made a little bit of mistake on the first version of the poster. And he will be talking about citizen science for mapping using free satellite data and open source softwares. So Dr. Kazuo Hirose, let's start.
Okay, thank you very much, Nobi-san. I'd like to share with all of you about citizen science for mapping using free satellite data and open source software. This one is not only for citizen science. Of course, the researcher can do similar approach using free satellite data and open source software. So what is citizen science? Citizen science is now a common word, but here you can see this term entered the Oxford English Dictionary in June 2014. Citizen science is defined as scientific work undertaken by members of the general public, often in collaboration with or under the direction of professional scientists or scientific institutions. So now, citizen science, this is very important to collaborate with professional scientists, because this activity can contribute to climate change actions from the citizen side. Okay, so citizen science is now important. How to perform the citizen science? We are proposing the zero cost approach. So this zero cost approach is very simple: to utilize free satellite image, open free GIS dataset, and open source software. So totally zero cost. And this one enable to accelerate mapping, monitoring mangrove and seagrass by citizen, local government, and researchers, all stakeholders. So zero cost is composed of three parts. First one, free satellite images. This one very popular, Landsat, Sentinel-2, MODIS, and PALSAR, SRTM, and open data. In case of blue carbon, we can use Global Mangrove Watch data. You can download this data and import to your computer. And open source software, there are many useful softwares, QGIS and Saga, and also now the handheld cell phone application is now very useful. So what is the open source software? The ArcGIS, this one, very popular and powerful commercial software, but QGIS, we don't need to pay the license. So free software, very useful for everyone. And also the field survey tool, now free, very useful applications are available for Android operation system, LoxMap, OSM Tracker, and iPhone GPX tracker, and iPhone and Android field note. This application was developed by our organizations. So zero cost approach can be shared with the citizens and all stakeholders through workshop. Workshop is composed of 3 parts: lecture, practice, and field survey. This one very important contribution by citizen, and data integration. So this is a photo or field work and collecting the field information. And now Dr. Ariel already introduced MVI for mangrove extent mapping is available. We can use this technique. Last year, we had 2 workshops in Jakarta and Manila. So one of important outputs, there are 2. Training module was prepared by participants quickly. Thanks for Ms. Karina and Mr. Farooq of ITB. This one, module pelatihan bahasa Indonesia. So everyone can start the zero cost approach for every field. And also WhatsApp group. This one was started from last year, June, like this. Everybody can exchange the information and follow up through WhatsApp groups. This one, the workshop Manila. So now I want to introduce some examples. Mapping mangrove by Landsat, and MODIS land cover, and field survey tool, LokusMap. This is the false color satellite image Landsat 8, RGB 567. If you display this combination for Landsat, the mangrove area can be highlighted, okay? But we have already the free data set. This one, the Atlas Mangrove the 2010, this one, USGS 2011, this one, the Global Mangrove Watch 2016. And also free satellite, free application, Saga. This is very powerful. The segmentation process is quickly performed by Saga. In this case, I classified 15 classes. So one of class is corresponding to mangrove. Then we can compare with this distribution of class 8, sometimes class 6, with the existing mangrove extent maps. So in this case, Global Mangrove Watch here mapped, but Saga cannot mapped because of the algorithm, and also maybe the resolution, I don't know, but some part cannot be mapped by Saga segmentation. But here, Global Mangrove Watch map error part. So this area, no mangroves. So we can compare with the result of segmentation by Saga with existing the mangrove extent map quickly. However, Dr. Ariel already introduced mangrove vegetation index now developed. We can calculate the mangrove vegetation index by this formula on QGIS or SAGA. So now we can start for mangrove extent mapping. And also here, land cover change. Already Professor Nadaoka explained. There are so many land cover changes. And now it is very difficult to find no concession land, no land cover change area, only few parts in Berau watershed. Okay, this is the very severe situation. We have to advise to local government how to protect, how to improve this situation. And this one, final slide, field verification by cell phone application, LocksMap, free application on Android. You can import, analyze satellite image to cell phone, and you can bring to all field. This application, no need to use telephone signal. So everywhere you can use this tool for field survey. Okay, thank you very much. That is my presentation. Okay.
Thank you, Dr. Kazuo Hirose, for the very interesting presentations on the zero cost of mapping. And lastly, we will have presentations from our guests from Australia. And here we have Dr. Andy Stephen. He is a director of CSIRO Ocean and Atmosphere Australia. And actually, he planned to talk about on the integrated assessment information system on blue economy, but due to limited time, he will focus mainly on the information system for blue economy. So Dr. Andy Stephen, please take the floor. Unmute. No.
Sensing as well as information, as well as modeling data. So I'm going to give you a bit of an overview of what the information systems are, why we need them, what are the principles and approaches, and then just give you two examples of information systems. The first one we call eReefs is an information system we've developed for managing the whole of the Great Barrier Reef. The second one really deals with aquaculture. So this was a project called SIMA that we developed for the Chilean aquaculture industry. So let me just give a quick introduction about why the blue economy. As we know, the blue economy is growing at a rapid rate, estimated to be $3 trillion by 2030. Every country has a different view about what the blue economy is. I don't want to talk about that here today. I just want to highlight the fact that blue carbon is an integral part of what we think of the blue economy, as is things like human well-being, social equity, unless we actually put in place the conservation and environmental management that underpins the sustainability of the various industries that we rely upon. This is what we need, and this is why we need blue carbon, better blue carbon understanding. So the key challenges around developing a blue economy are really fourfold. One, with growing industries, trying to manage MPAs, we need to better assess cumulative impact. The second one is that we can think of coastal ecosystems as broader socio-ecological systems, where we need to understand not only the natural asset, but we need to understand humans' roles in it in terms of livelihoods, in terms of things such as governance, the role of infrastructure, trying to understand that. The third one is really, how do we predict the future? And we don't want to predict the future, we actually want to better project the future according to a range of different scenarios. And we're seeing that now as we live in a COVID world. What are the scenarios by which our world are going to look like? Lastly, in terms of thinking about the blue economy, we need a better national accounting system, and we saw a very good example of that today in terms of the national carbon inventory systems that have been developed in Indonesia.
Excuse me, Andy, can you make it full view, full screen?
Oh. Okay, I think I'm on the wrong screen, sorry.
That's okay.
Is that better now, Novi?
Still not in a full screen.
Okay, I think I've got to change.
Yes, no, not yet. I can see you, but not your slide yet. Okay.
This one?
Let's wait.
Can you see that one?
Yes, perfect. Thank you.
Sorry about that. Sorry, I was on the wrong screen.
That's okay.
So how do we build better information systems? So really, as I've said, this is about the integration of having more efficient and effective observations, whether they're drones or in situ continuous sensors, taking some of that data and integrating it and assimilating it into a range of different models. And we've seen some of those different models today. So this is what I'm talking about when we're talking about coupling of models that might be hydrodynamic models, biogeochemical models, as well as catchment models, and then species-specific models. So, but then beyond researchers that have an interest in running these models, we actually want inputs in there that help us to make better management decisions, whether it's better managing carbon, protecting the Great Barrier Reef. But in order to do that, we also need then to better communicate a set of services. And really what we've seen in recent years with information systems is the ability to deliver a set of customized services that can be used by a whole range of different users. And I'm going to show you some examples of those. So just the concept of an operational information system, as I said at the top of this particular slide, really we're talking about a range of services that could run from real-time information as we produce through to thinking about different scenarios, land use practice, climate change. We might want to use an information service to tell us about different reporting, so compliance and assessments, water quality information. Occasionally, and unfortunately, we get incident responses like we're seeing in Mauritius, so dealing with oil spills and other maritime incidents, through to better forecasting events such as coral bleaching or floods and storms or safe navigation for vessels. But really, a lot of people don't want to see what's below this area that I've highlighted as discovery, and here I'm showing you the eReads platform. So here we've integrated a set of different regional models, higher resolution relocatable models, remote sensing, as well as a range of other information, some of which is internal to organizations, some of which we access from across a range of different institutions, and we bring that together to deliver those services I'm not going to go into any of the models or talk about any of the detail, other than to hopefully you'll understand what I'm on about here, and really to say that it's supported by both an interoperability pillar, if you like, on the left-hand side, as well as a validation and verification system that gives us trust the system is working. So a couple of examples here. So eReefs is a system we developed for the whole of the Great Barrier Reef. It has a range of different models that run. It runs a regional model of 1 kilometre, and then it downscales to a set of high-resolution models. It integrates a range of different Earth observation and in-situ products. The sorts of services we can get out of that are, for example, hydrodynamic model uses that might look at catchment connectivity. Over here, we're looking at salinity distributions. So we're producing exposure maps of different things. We can look at shelf exchanges of how water masses are coming onto the Great Barrier Reef. And within that, we can then look at various scale features. We might want to look at the incidence of crown of thorns or jellyfish dispersal. So understanding the connectivity between the systems is important, as well as looking at things such as upwelling of high concentrations of nitrate onto the reef. We can use that information to then derive a set of products that are useful to management. So here we're assessing water quality by integrating both remote sensing information and modelling information to produce the typical report cards that you see by regions that then allow us to look at the compliance of different regions as to whether they're meeting the set water quality criteria. On the scenario front, we can then also use the model to ask a set of questions, and here we're comparing what was it like before Europeans arrived in Australia versus the current set of conditions. Again, we can do this for regions, and we can look at the effects of different scenarios. If you like, if we were to change a land use practice by 50% reduction in sediment, for example, what would the effect be? So again, another set of very useful sets of information that can be used. In terms of looking at where it might bleach on the Great Barrier Reef and trying to get organised for that, again, the models can run in 2 to 3 day forecasts, and we can also look at bleaching there and predict which are the areas that are most vulnerable. Lastly, we can use it around looking at carbon chemistry. So ocean acidification is a major issue here, trying to understand, again, what is the vulnerability of different parts of the reef at different times of the year to ocean acidification. The other model example I want to show you is the work we do in Chile. So this is, again, an area of a similar size, about 2,500 kilometres, that we did looking at the aquaculture industry. The key difference here is while eReefs was very much focused around this biophysical modelling and data and information, in this particular study, we wanted to incorporate some of those broader socio-economic elements that I talked about before. So understanding the productivity of aquaculture, understanding what were the economics of aquaculture and how they got affected by different things, understanding the role of humans and different user groups in terms of the overall sustainability of the aquaculture system. So again, very similar in terms of the biophysical models. To that, we added some connectivity models that allowed us to look at changes between and spread of disease between different farms. We developed some ecosystem models that incorporated some higher level megafauna. We incorporated farm models that really allow us to look at disease and capture that within a risk model. The access to all of this information is through a very, a web-based portal. It's familiar to people. You can click on different things and get to the information you want very, very easily. Here I'm showing you, as an example, some of the bioeconomic information here. So again, you can do scenario modeling where you can change a number of different parameters by different region in terms of the price of the actual fish, what the discount rate is, what it's costing you for feed. That allows you to look at a range of scenarios and work out what is the most operationally effective method for you. At the whole of system modeling, again, we can look at things such as megafauna interactions. For example, sea lions are very important in Chile, as they often come in and break the nets open and eat the salmon. So understanding those sorts of things, again, and sorry, this is in Spanish, but again, you can look over a period of time, a whole range of different, if you like, dashboards about how the system would be tracking. The connectivity model really allows us to look at particle dispersion, so we can identify areas of high risk where there might be disease transmission from one site to another, and really allows you to take effective action before we see such incidences. So hopefully that's given you a bit of an overview of information systems and how they can be applied. We are currently developing some for blue carbon, both in Australia and Papua New Guinea and Fiji, where we're currently working, and happy to talk about that some further. Thank you.
Thank you very much, Andy. Everyone, so we have come to the end of the webinar. So actually, we were planning to display all the Q&A that you have typed in, and some of them have been answered by our speakers, by some of the speakers. But since we are behind our schedule, then we will just complete that. We will follow up with your questions. And if there are some that have not been answered by the speakers, we will ask the speakers to answer your questions. Because, for example, Dr. Saiful Anwar and Mr. Andi Rusandi, they have left the webinar room due to some other important commitments. So I think all of the questions directed to Mr. Andi Rusandi and Mr. Saiful Anwar have not been answered yet, but we will follow up with that. And we will compile all the questions and answers in one file, and then send it to you along with the materials from the presenters. Okay. But now, allow me to have a direct Q&A. So I will invite maybe 2 or 3 participants to raise their hand. So if you have questions, please raise your hand using the participant toolbox at the bottom of the webinar Zoom applications, please. Okay, let's see. Okay, we have maybe this Mr. Kangkuso Analudin. Okay, so please, Mr. Kangkuso Alanuddin, to give your questions. Yeah, Mr. Kangkuso. Okay, Mr. Kangkuso, can you unmute your microphone?
Okay, thank you. Okay. I already unmute.
Yeah, please take your time, Mr. Kangkuso. Yeah, please direct your questions to the process for your questions.
Kita pergi di landing di LPPN yang lantai bawah itu, ada dokumen saya mau periksa, kita ambilkan.
Okay, so let's move to the. Sorry, I think maybe it sounds that he's being occupied. Let's move to the next person for questions, for direct questions. Mr. Nur Salim Natsir. Mr. Nur Salim Natsir, are you ready for your questions? So anyone who wants to ask questions directly, please raise your hand by clicking the raise hand functions under the participation test box. Mr. Nur Salim Natsir. Okay, let's move to the next one. We have Mr. Agus Salim here. Can you hear us, Mr. Agus Salim? Agus Halim, sorry. Mr. Agus Halim.
You can hear me?
Yes, yes.
Yes. Yeah.
Thank you.
I'm Agus Halim from Syah Kuala University. So I think it is very important coastal ecosystem can absorb greenhouse gas. So I think the coastal ecosystem can function to control over the greenhouse gas in the atmosphere. So I think very important how to know the carbon dioxide come from. This is come from near atmosphere or come from the long distance atmosphere, maybe from the outside of the location, maybe from other province or other countries maybe. So it is very important to know exactly about the benefit of the coastal ecosystem to absorb greenhouse gas. Because of that, we can give a word for the location to how to control or to develop the conservation program for the coastal ecosystem. So it is related to the presentation by Mr. Masaya and also Andy Seven about the monitoring control. I think we have to design about the MRP program, monitoring, reporting, and verification. So it is very important to make high trusting for other countries to make green investment, especially related to the coastal ecosystem program. As we know, the coastal ecosystem program like mangrove, this is the specific location, not exist in outside of the tropic countries. Thank you very much.
Thank you, Mr. Agus
Halim.
Yeah, Agus Salim. Maybe Andy, could you have some comments on that?
Yes, thank you, Agus, for those comments, and yeah, couldn't agree more. There's a lot we're doing. Let me go to, I guess, what's happening at the global level. As you know, there's a high-level panel meeting going on, and so some of the key themes coming through are around how do we take different systems like, you know, nationally determined contributions, how do we couple that with a range of other strategies, particularly in a COVID world where nations are going to be rebuilding, to really bring in concepts around conservation, the use of blue carbon, the use of green and blue infrastructure and restoration to really start to rebuild systems, and having a broader view of the resilience of coastal ecosystems that includes not only their structure and function, but also the livelihoods that are part of our dependency upon them. Thank you.
Thank you, Andy. I think I'll invite another participants to ask directly to the speaker. Please mention your name and affiliations and to whom you direct your questions. And please make it short, okay, to the point. And we have Nur Alim Natsir. Mr. Nur Alim Natsir, are you ready for your questions? Mr. Nur Alim Natsir. Okay, so How about Mr. Kangkuso Analudin? We will unmute you.
Okay.
Questions?
Hello.
Mr. Kangkuso, can you hear me?
Yeah, I hear you.
Yeah, please. For your question, are you ready for your questions?
Oh, I didn't. I want actually to have some discussion with Professor Kazuo Nadaoka, if it's possible.
Yeah. You have questions for him?
Yeah.
Okay, so please direct your questions and make it short, please.
Yeah, thank you so much for the time. Actually, I didn't join from the beginning of the discussion, but because of the meeting at office, I think first I want to say hello to Professor Kazuo.
Yeah, thank you very much.
Yeah. Actually, we have a discussion last time. I think if the possibility to establish plot for monitoring of the seagrass in Southeast Sulawesi. So, is it still possible to? I mean,
yeah, definitely.
Okay.
Yeah.
Only that. Yeah. Thank you.
Why not?
Yeah.
Thank you, Mr. Kangkuso. And you are from which institution are you affiliated with?
Yeah, I'm from Halua University.
Okay.
Yeah, actually we have a collaboration with Professor Kazuo Nadaoka started in 2014 until now, funded by Ministry of Higher Education. We also work in blue carbon, and this time we are working in ocean acidification.
Thank you. Thank you. Yeah. I think Nadaoka Sensei used to inform me about that. Thank you.
Yeah.
Thank you. And we are now around 10 minutes to 12:30 Jakarta time. So I think we have to put in 12:30, and there are like 10 minutes remaining, 10 minutes left. So let's invite another participant for question. So if you would like to have questions directly, please raise your hand using the raise hand functions in the participant chat box. So yeah, Miss Adriani Mutmainah. Okay. Are you ready for your questions?
Hello.
Hello. Yes, we can hear you. Yes. Please supply us with your information on your name, affiliations, and to whom to direct your questions. Please.
Okay. Thank you very much for your time. As you know, my name is Adriani Mutmainah, and I'm a doctoral student of Hiroshima University, but recently I'm in Indonesia. And I'm doing a research about seagrasses in Miyajima Island, Hiroshima. But I'm trying to do the phylogenetical and ecological analysis for the seagrasses in there. But I'm not. I also want to learn about it because I'm trying to make the similar research with the seagrasses in my place in Indonesia, in Makassar. But the problem is when I also want to try to make seagrasses mapping around some small island in here, but there's not so many data that I found about the mapping in here, because as we know, when I trying to figure out by using the Google Maps, I it's a little bit difficult for me to distinguish between the seagrasses and the coral or another another organism around the seagrasses. So I mean, I want to learn more about it because I think it's very important for us to improve our data. To put the data correctly, since there's not so many big data about the seagrasses in here. Especially there is one seagrasses in Makassar. Around Sulawesi Street. It calls Halophila Sulawesi, and I want to try to do it. So maybe I don't know to whom I direct this question, but how can I try to? I mean, I want to make a mapping about these seagrasses since it's not so many data about it. So I want to learn it. So to whom I need to ask it, I don't know exactly. Sorry, because I saw so many material today about seagrasses, and I'm confused to whom I should to ask about it.
Okay, thank you, Miss.
Thank you.
Yeah, thank you for your comments and questions. So for your informations, maybe I can answer some of your questions. For your informations that have a system like the national data custodian, okay, and the national data custodian for seagrass, the spatial data for seagrass, the Indonesian national data custodian for seagrass is the Research Center for Oceanography, LIPI, yeah, University of Science. But I'm also working with them, and SATREP's Blue Carrier project is also working with them, but we have not had yet the national mapping of seagrass.
Okay.
At least have some data, some various data from their research and from our, and because they are the national data custodian for seagrass, they have this data. So since they are official data custodian, you can try to contact them, and then to figure out how to help you. They have some guidelines for benthic habitat, yeah, and maybe you can contact them and then have some information about the seagrass data. And maybe I like to invite Matt to have some comments on the maybe mapping aspect, the challenge, since yes, mapping benthic habitat is challenging compared to the still one.
Yes, thank you, Novi. Hello, Adriani. Thank you for your question. I think, well, first of all, I'm really pleased to hear that you're grappling with the problem, and the more information, the more sites we have, the better. I'm really pleased to hear that you're looking at it in Makassar. You've touched on a problem that many of us are grappling with: how to map seagrasses. It's a tricky problem, especially for Halophila. You mentioned Halophila Sulawesi. Halophila is particularly challenging because it's so small and difficult to detect. I could give you some clues, but perhaps what I'll do is make an invitation. If you contact me by email, okay, I will put you in touch, and we can have a more detailed conversation. But in terms of a general answer, Novi has made a good suggestion. The guidelines in the report that of LIPI, led by Suzy Rabawati and other co-authors, is a good place to start. If you look at that, and then we can start thinking about other options, perhaps using some of the free data that was mentioned earlier.
Oh, okay. Thank you very much, and I would like to have your email later.
Yes,
Okay, I'll pop it in the chat
you
now.
are already in another meeting. Do you want to left and join the meeting? No.
What? Sorry?
Okay, thank you, Matt, for your comments on Adriani's questions. So I think now 1 minute to 12:30, so we have to conclude our webinar. But before doing that, I would like to bring up some pollings again. Okay, so please get ready, dear participants. So polling number 2, please bring it up. It is a simple questions. Okay, where are you? Where are you? Okay. I'll count 5, and then we close the polling and see the results and move to the next pollings. 1, 2, 3, 4, 5. Okay, stop the polling. And the result is Java in Bali. Okay, thank you. And we move quickly to the next one. And the third polling, polling number 3, please bring it up. Yeah. What is your theme of interest? Climate change, conservation, or both? I'll count to 5 and then close the polling and see the result and move to the next one. 1, 2, 3, 4, 5. Okay, let's close it and see the result. Okay, so most of the participants are interested in both aspects. Okay, move to the next pollings. Polling number 4. Please bring it up. Yeah. Similar to the previous pollings, but maybe it is directly related to your work. Do you involve in climate change, conservation, or both? It's 1, 2, 3, 4, 5. Okay, let's close it. Oh, no. Thank you. Okay, so we have both. Okay, climate change and conservations that are mostly related to your work. Second, conservations and climate change. All right, so move to the next polling. So this is about the whole sessions that we have been through. Yeah, the most interesting sessions for you. Which one? Policy sessions that was delivered by Mr. Saiful Anwar and Mr. Ani Rusandi. Keynote speak sessions delivered by Professor Nadawaka, or technical sessions. I'll count to 5. 1, 2, 3, 4, 5. Okay, let's close the sessions. Okay, and the result is the technical session, which is most interesting one to you. The next, moving to the next one, the next polling. Yeah, for those who have selected technical sessions as their interested one, which aspect that you are mostly interested in? Remote. Actually, these are the subjects delivered by the presenters under the technical sessions. All right, I will count. There's no right and wrong. There's no right and wrong here. Please feel free to select which one interests you most. I'll count to 5. 1, 2, 3, 4, 5. Let's close it. Okay, and most of the participants are interested in seagrass ecology and conservation. Oh, interesting, right? Okay, and then remote sensing. Okay, the next polling, number 7. We will still have more. We have 8 pollings. Let's bring up the pollings. similar one, but which one is the most relevant to your work instead of just interesting to you? Which one is most relevant to your work? Which one is most relevant to your work under the technical sessions? Okay, I will count to 5. 1, 2, 3, 4, 5. Let's close the polling. Okay, still the same one. Okay, now the last one. This is for our future webinar. Let's bring up the last polling. Okay, for the next Blue Carbon webinar, what topic you would like to suggest? Which one for the next Blue Carbon webinar? Yang okay. Okay, I will count to 5. 1, 2, 3, 4, 5. All right. Okay, thank you very much for your active participations to the polling. So we have informations about you. We have your inputs or opinions sessions, and we also have your opinions on the next Blue Carbon webinar. So I think we have to conclude the sessions. We are behind our schedules. Thank you very much to all the speakers. We really appreciate your time and your knowledge sharings to this webinar, and to all the participants who have joined this webinar, and particularly to the participant who stay with us from morning to this afternoon time. So thank you so much again to the speakers and participants, and I hope we can meet your expectations of the webinar, and see you in the next webinar. And please stay healthy and happy, and have a good day. Goodbye. Thank you. Bye-bye.
Thank you. Terima kasih. Goodbye.
Thank you.
Terima
Novi-san.
kasih.
Bye.
Thank you.
Thank you very much.
Yeah. And you can see the link for the webinar in the chat box, and we will send you the materials. Yeah.
Oh, matur suwun. Amit. Bye.
Yeah. We will still open the webinar room for the next 30 minutes, but if you want to leave, please feel free to do so. Thank you so much. Thank you so much.